afternoon. My name is Professor Duke Orata. We are continuing with our lectures. We are still in the steady flow and jet propulsion, so we are continuing our lectures. And today we want to look at convergent nozzles. We have had a series of lectures, and I keep encouraging you that you go through them so that we build up systematically in our knowledge in these particular discussions which we are having. And one of the things is that we have been looking all along now, we've been looking at area changes which will actually accommodate continuous isentropic expansion of those fluids from some initial state to some final pressure. That is, we have been considering, changes in area which allow or accommodate continuous isentropic expansion from some initial state to a final pressure. And so we can illustrate this, what we are saying diagrammatically. Let's illustrate it diagrammatically. Let's have let's call this unity as a 0 pressure ratio P1. And let's just have our nozzle there. Let's call that plane 2. Let's say the initial state, and we have the downstream pressure. So in this particular diagram, the initial state is kept constant, and we have the downstream pressure which we are denoting as P subscript E. And in the beginning, the downstream pressure is equal to the initial pressure, that is P1. So just note that the initial state of the system is kept constant. That's point number one. And you need to note that initially the downstream pressure, PE, let's note there that downstream pressure, that's what we call PE, downstream pressure, is the same as P1. So when downstream pressure PE is equal to P1, what does that mean? That means that there's no pressure differential, so there will be no flow. There's no pressure differential, so there is no flow. Therefore, no pressure differential, therefore no flow. And that's very easy. We are saying that the pressure, the downstream pressure and P1 are the same. There is no pressure differential, so basically there will be no flow. So if we represent that curve here, let's represent by curve 1. Let's call that curve A. So there's no flow. This is curve A. Here, PE is equals to P1, and that is equals to P2. And what is P2? P2 is the pressure at the plane of the exit of the knob, of the nozzle. P2 is the pressure at that plane, P2 at the exit of the nozzle. So again, let's note that P2 is the pressure at plane 2 at the exit of the nozzle. So we are saying that there's no pressure difference at that particular point. So what we're going to have is that there will be no flow. Now, when you open the valve and the downstream pressure starts reducing, when you open the valve and the downstream pressure starts reducing, then you will notice now that the axial distribution of pressure will be in the form of a curve. So when you open the valve, and the downstream pressure reduces, the distribution of the pressure at the axis, or the axial distribution of pressure, will be in a curve form. So we can illustrate that. Let's call it curve B. Let's call it B. So we have curve form B. So what are we saying? We are saying that PE will of course be equal to the pressure at the plane, at the nozzle exit, and it will of course be greater than the critical pressure. Remember, we have talked about critical pressure quite extensively in the earlier lectures, where we have talked of the CPR, that's the critical pressure ratio, and we know that the critical pressure ratio, we said that the area is minimum at that particular point. And so we will have that curve there. Now, remember at this particular point, PE over P1, so we have here PE, so we have here P, this is distance, that's distance. So what we are saying is that at this particular point, PE over P1 is less than PC, is greater than PC over P1. And so we will have that curve form, that particular point. Now, but when PE is equal to the critical pressure and is equal to P2, we will have that state. And remember, as we are having these changes here, the mass flow rate, also note the mass flow rate, the mass increases. And so we can have that form also represented. We can represent that here. We can have our mass. It increases. It increases. So in this particular region, remember here, this particular region, we are saying that PE is greater than PC. So we have still not reached our maximum flow. And so at the point where the downstream pressure equals the critical pressure, which also is equal to, because the pressure at the plane, the exit, the nozzle, will be constant and will be equal to PE at that particular point, the downstream pressure, which we are saying at that particular, when it will be equal to the critical pressure, then at that point we'll have the maximum mass flow. Let's just Write that down. So we are saying that as PE reduces, the mass flow increases. We reach maximum mass flow when PE is equals to P2 and is equals to PC. Remember, PC is the critical pressure. So that will be the maximum. At that particular point, that will be the maximum. Where we are saying here we have PC over P1. That is the CPR. That's the critical pressure ratio. And of course, above this, we have PE is less than PC. About that. So we have maximum flow at that particular point when PE, that's the downstream pressure, is equal to the critical pressure, which is also the same as the pressure at the plane at the exit of the nozzle. And so we can represent that with curve, let's call it C for consistency. So we have curve C. There PE is equals to PC, and this equals to P2. Now, we can't reduce, we don't want to reduce PE further. We can't reduce PE further because basically we are saying that we don't want to reduce PE further because it cannot be less than that critical pressure ratio. Unless, for example, we are saying that we are having another throat upstream of that plane 2, then probably we will be in that kind of situation. So what we are saying is that the ratio PE or P1 should not be less than PC over P1, unless, I'm putting that dot there, unless we have another throat upstream of plane 2, unless we have a throat upstream of plane 2. And remember plane 2, we said that was corresponding to the plane 2, we said corresponds. Plane 2, we said corresponds to that plane at the nozzle exit. So we have our C there. We have our C at that particular point. So basically, when we are at this point, there will be no change in the velocity, there will be no change in the specific volume and the mass flow. So basically, the nozzle is choked. The nozzle is choked. So we are saying that under these conditions, there is no change in velocity, in specific volume, or mass flow. So basically you can say the nozzle is choked. And like we have said, if, for example, you are to reduce PE further, if you are to reduce it further, then unless there is a throat upstream of that plane at the exit nozzle, then you will attain that. But other than that, we are going to have the nozzle choked and those changes will not be there. So that even if you are to have those changes, they will be so erratic. So that you'll have them erratic and they will be oscillating around PE. They will be oscillating around PE. So that what will happen is that the supersonic flow which you had after the divergence will ultimately now be reduced significantly as a result of viscous friction. And so we will stop at this particular point. We will look at convergent, divergent nozzles and see when the downstream pressures differ from the pressures corresponding to the dimensions of the nozzle. And that we'll discuss in our next lectures. Thank you.